This is Unit 3, Topic F. We'll be talking about linear approximations and differentials. First of all, linear approximations. The good news here is you actually already know all the math you need to do these. This is just another word for something you already know. Here's the concept. If we stay close to a point, a f of a on our graph, then the graph y equals f of x is going to stay close to the tangent line at x equals a, if we stay sufficiently close again to the original point. This is going to allow us now to use the equation of that tangent line as a way to approximate the values of f of x itself, again for x values that are close to a. Here's an illustration of what I mean. Here we've got a graph of f of x equals the square root of x. And we're going to go ahead and say, let's go ahead and draw the tangent line at x equal 1. So here we are at x equal 1, and I'm just for now going to sketch in the tangent line. We'll calculate it in a minute, but we can approximate it pretty well. So there's my tangent line. Here's what that paragraph just said. If I stay close to the point of tangency, x equals 1, so I move over just a little bit, the actual y value on the curve is going to be very close to the y value on the tangent line, right? These are really close together. Now if I go further away, of course the y value on the curve and the y value on the tangent line will no longer be really close. But as long as I stay close to x equals 1, the square root curve and the tangent line have almost the same y value. What that's going to allow me to do is use the tangent line to approximate the values on the square root curve. That's why we call these linear approximations. So when you see linear approximation, think use the tangent line to approximate. So that's what I meant when I said you actually already know all the math that you need to know to do this. What this is going to come down to is finding the actual equation of the tangent line and then just plugging in the x value that we want to do the approximation. So let's try it. In part A, it says to actually find the linear approximation to f of x at x equals 1. We've already kind of sketched it, but we'll verify that we sketched the right line by finding that linear approximation, which is nothing more than the tangent line. So as always, to find a tangent line, you need a slope and a y-intercept, or slope and a point. Our slope is always our derivative. And in this particular case, I probably pulled this down a little too far. The function was the square root of x, also known as x to the 1/2. So our derivative would be 1/2 x to the negative 1/2, or 1 over 2 square root x. I'm finding my slope specifically at the point where x equals 1. So I'll have 1 over 2 square root 1 for a slope of 1/2. Our point, they gave me x equals 1, and to get the y value, I plug back into the original function, which was the square root of x, so square root of 1, and my point is 1, 1. So to get the tangent line, y equals mx plus b, I would have 1 for y, 1/2 for m, and 1 for x. So 1 minus 1/2 will give me 1/2 for b. So my tangent line is y equals 1/2 x plus 1/2. We are now calling that the linear approximation, but it's nothing more than the tangent line. Okay. By the way, notice over here that's not too bad. My y-intercept was about 1/2 when I sketched that. And if you go a slope of a half, that would be a rise of 1 and a run of 2. Looks like we sketched a reasonable approximation. All right. In part B, it says use your linear approximation to actually get approximations for the square root of 1.1, 1.5, 2, and 3.5. So let's go ahead and for each x value, I'm going to do the linear approximation, which we just calculated. That was y equals 1/2 x plus a half. And then we'll compare that to the exact value of the square root of x, just to kind of see how well we're doing. Right? So the first x value I wanted to plug in was the 1.1. If I do the linear approximation, 1/2 times 1.1 plus a half, and you're welcome to use your calculator to do that, I get 1.05. If I plug the 1.1 into the actual exact value, so the square root of 1.1, I get 1.0488, etc. And so you can see that the linear approximation was really darn good, right? Very, very close to the exact value. That's not surprising because 1.1 is really close to our point of tangency, right? 1.1 would be around here. And so at that point, my tangent line and my curve are very, very close together. All right, let's do a couple more. The next x value that we're asked to plug in is 1.5. And again, I'm going to go ahead and plug it in first to the linear approximation. 1/2 times 1.5 plus a half. And that should be 1.25, yeah. Let's see how close that is to the exact value of the square root of 1.5. On the calculator, that's 1.2247, etc. So notice, not quite as close, but still not terrible, right? We're off by about 3/100ths. This one, if I rounded off to the nearest hundredth, would have actually even been exact. We're not off until we hit the thousandths place, but this is off by about 3/100ths. But again, still not too bad. If you think about that one on the graph, 1.5 would be around here. And my tangent line and my curve are still extremely close together at 1.5. So we should get a reasonable approximation. All right, a couple more. Next x value is 2. So if I plug that into my linear approximation, 1/2 times 2 plus a half, that'd be 1.5 or 1.5. And the exact value of the square root of 2 on the calculator is 1.4142, etc. Notice that the approximation is starting to pull away from the exact value. We're now about 1/10 off. So not the best approximation anymore, but again, not especially surprising when you think about the fact that over here at x equal 2, my tangent line and my curve are starting to be visibly different in their y values. All right, one more. The last x value is 3.5, and you might ask yourself, are you expecting a very good estimate here? But let's try it. I'll plug that into my linear approximation. 1.75 plus 0.5, that'd be 2.25. Okay. Clearly not a good estimate for the square root of 3.5, because that's got to be less than 2. It's actually 1.8708, etc. Okay. So a very poor estimate here, not even close to the exact value. And again, that shouldn't surprise us at all, because by the time we get to x equals 3.5, our tangent line and our curve are quite far apart. Those y values are not close to each other. So, linear approximations can provide a really good way of estimating function values as long as we pick x values that are close to the point of tangency. Now you might ask, why would you care about this? And the answer to that is actually a little bit of a historical answer. In reality, with calculators today, just plugging in a number and getting the square root of x is not a difficult thing to do on a calculator. But keep in mind that back when calculus was invented, we didn't have nice calculation devices. A problem like finding the square root of 1.1 was a really long algebraic process, and a linear approximation often provided a really nice quick way of getting a reasonable result in a hurry. All right, let's try another question. We're going to stick with this function, the square root of x, and I actually want to look more at this last result. We saw that our linear approximation did not do a good job of estimating the true square root of 3.5. Could I use a linear approximation to approximate the square root of 3.5? Well, the answer to that would be yes, but not the linear approximation that involves the tangent line at 1, right? I'd be much better off doing a different tangent line, one that's closer to 3.5. In fact, if I drew the tangent line here at 4, that would get me really close to the point I wanted. So that's going to be our strategy to actually approximate 3.5 much better. So let's use the linear approximation, or in other words, the tangent line, at x equals 4 instead, because 4 is close to 3.5. The other reason that I chose specifically 4 is the square root of 4 comes out evenly, so it's going to be an easy number to work with. 3 would have also been close to 3.5, but the square root of 3 doesn't come out evenly, so I'd rather not use it. So when you're choosing the point to do your linear approximation at, you want to pick a point close to the value you're looking for, but also a point that works out really nicely when you plug it into your function. All right, so here we go. Our slope is our derivative, and it's still the square root, so it's still 1/2 x to the negative 1/2, or 1 over 2 square root x. But now I'm plugging in x equals 4. So 1 over 2 times 2 would be 1/4. So there's my slope. My point, they gave me x equals 4. Y is the square root of x, so the square root of 4 or 2. And my point is 4, 2. So my linear approximation or tangent line, y equals mx plus b. 2 equals 1/4 times 4 plus b. Looks like b is going to be 1. So my linear approximation, y equals 1/4 x plus 1. Now if I want to actually approximate the value of 3.5, I probably should have left myself a little more space there, sorry. I can plug the 3.5 in here. So to approximate the square root of 3.5, I'll take 1/4 times 3.5 plus 1, and I get 1.875. Notice that's a much better approximation, right? Before we had the square root of 3.5 was 1.8708, much closer to this value than what I got with the linear approximation at 1. And it should be. My tangent line at 4 is going to be very close to the curve at 3.5. All right, let's do one more of these. In this next example, we'd like to use a linear approximation, first to estimate the sine of 0.1, and then to estimate the sine of 2.5. We're going to have to pick our own x values for the tangent lines. So when I'm thinking about 0.1, of course that's very close to 0, and sine 0 is easy to do. So I think I'm going to do this first one using a tangent line at x equals 0. All right, slope would be our derivative. And by the way, notice that this function is just y equals sine x. That's what I'm trying to approximate, and that's what's graphed here too. Y equals sine x. So the derivative would be cosine x. And if I plug in my x equals 0, cosine of 0 is 1. So my slope is 1. For the point, x is 0. To get the y, I plug in here, so sine 0, which is 0. So the point is 0, 0. Plugging into y equals mx plus b, 0 equals 1 times 0 plus b, so b is 0. And my tangent line would just be y equals 1x plus 0, or just y equals x. So, if I think tangent line here, the simple line y equals x is my tangent line to the sine curve at 0. And that means that if I want to approximate the sine of 0.1, I'm just going to use y equals x, and I'm going to get the x value, 0.1. In fact, that's a handy little approximation to know. If you're in radian mode, the sine of any really small angle is approximately equal to the radian measure of that angle. So I could probably say, like the sine of 0.04 is about 0.04. The sine of 0.21 is about 0.21, right? As long as you stay pretty close to 0, the sine of any angle is actually equal to the value of that angle in radians. Let's just double check. I am in radian mode. And if I did do the sine of 0.1, notice I get a very close approximation here. It's 0.0998, so I'm off not until the 10,000ths place here. So I'm off by about 2 10,000ths, so really, really good approximation. Now, that line, y equals x, that's tangent to this graph at 0, is a great approximation, close to 0. In fact, you can see how close we are near 0. But it would be a terrible approximation at 2.5. The graph has started coming down there. So we need another point of tangency. to do that approximation. So I want a new tangent line. And I'd like to pick something close to 2.5, but something that I know how to plug into my sine function, something that I can do exactly. In order to do that, let's think about the unit circle. It would be great if I'd pick an angle that's equal to one of these, because then I could just read the sine function right off of my unit circle. So let's find one of these angles that's somewhat close to 2.5. Obviously pi is 3.14, so maybe I go backwards from there. Let's try 5 pi over 6. It's 2.6, it's not too far away. What about 3 pi over 4? 2.35. I think this one's actually just a little bit closer to 2.5. So let's use 5 pi over 6 as our point of tangency. Our slope, again y prime, was the cosine of x. And if I plug in 5 pi over 6, the cosine of 5 pi over 6 is negative square root 3 over 2. Okay. By the way, I kind of like that. Notice at 2.5, the slope should be negative. So I like that slope. I am going to go ahead and get a decimal approximation for it so I can use it in my line a little bit more easily. It's about negative 0.87. The point, x is 5 pi over 6. Y is the sine of 5 pi over 6. And the sine of 5 pi over 6 would be 1/2. Let's get a decimal approximation for the x. It's about 2.62. So my tangent line, my linear approximation, y equals mx plus b, would be 1/2 or 0.5 if I'm using decimals, equals the slope, negative 0.87, times the x value, plus b. That's negative 2.28 plus b. Adding it over, my b value is going to be 2.78. So my linear approximation is y equals negative 0.87x plus 2.78. Now I specifically wanted to use this to approximate the sine of 2.5. So I'm going to go ahead and plug that 2.5 in for the x. And I get 0.605 as my linear approximation. If I grab my calculator and actually do the sine of 2.5, I get 0.598. So again, not too bad. What is that off by? About 7 thousandths or so, 0.605? Yeah, it's off by about 0.65 thousandths even. So it's a pretty good approximation to that value. And again, not surprisingly, because I picked a point at the beginning that was close to the point that I was trying to approximate. All right, so linear approximations are really nothing more than using the tangent line to approximate the y values on the curve. We will stop there and come back and talk about differentials in the next video.